Check it out now, y'all.
NanoHub U, online instruction.
Welcome back. We are discussing potentiometric sensors. And if you remember that we started with this basic notion that a potentiometric sensor this response should scale linearly with analyte concentration. That if you increase the analyte concentration by a factor of 100, your current goes up by a factor of 100. That was our hope. Turned out that salt was a necessary evil, necessary because it allowed the DNA to stay together, the protein and the antibody to bind. Salt was essential through screening. However, it was evil in the sense that for the price it required for the salt to be there, was that essentially it took away 90% or more of the charges for itself, allowing very little to be available for the sensor. And in fact, this so quote-unquote tax went up as the analyte density increased, and therefore, hence the log dependence. Now, in the last lecture, we talked about the second problem associated with a fluid like water, and that had to do with pH. Now, in the last lecture, we said that how that dependence, the surface charge dependence on pH, could be used for a positive purpose, which is to use it as a pH meter. But in this lecture, I want to come back and show that pH also plays a sort of a negative role in terms of biomolecule detection. And this is very important because many times experiments are misinterpreted if you are not careful. Now, at this point, you might say that, Professor, I'm not going to put any orange juice in my experiment. I'll be really careful. But it doesn't matter because even pure water has pH of 7, and that itself can cause trouble. So that's the introduction. Let's get started. I'll begin by explaining how the DNA charges depend on the pH. We'll talk a little bit about the protein, very similar physics, and I hope you will understand them easily. And then we will pull all these things together. Surface charges, the DNA, the protein, and see how a MOSFET underneath actually views the whole system. And is there any way to get rid of the surface charges so that you can see the biomolecules more clearly, sort of quote-unquote more clearly? We'll explain. Very brief reminder, you may remember that a biomolecule, like a DNA, is a polymer having many similar type of units. And these units are bases, for example, identified by bases called A, T, C, and G, 4 letters. And what we found was that there was a central sugar ring. There was this base, which could be A, T, C, G, any of the 4. But the charges, I said, was really coming from this PO4. And this PO4 came because this is a phosphoric acid, residue of the phosphoric acid. It lost its hydrogen and became positive in the process. Let me explain how that happens. You see, each one of the residues associated with A, T, AA, for example, and G, each one of them, there is a phosphoric acid molecule associated with it. Now in water, remember everything we are talking about is in water, it may reduce 1 proton, it may sort of get rid of 1 proton, 2 proton, or 3 protons. So whatever number of original molecule you had in the dry, essentially will become charged when you put them in water. And this is the corresponding picture. This is neutral. You can see the 3 white hydrogen atoms hanging around. Here you see 2, here you see 1, and here you see nothing. So therefore, charge 3, 2, 1, and 0. How do I calculate the relative proportion? Because remember, overall, that will determine what my charge of a biomolecule is. Once you know your pH, of the solution, then everything becomes easy. This is how. So let's think about how it goes from a completely neutral to charge 1. These dissociation rates are all known from experiment, and in this case the value is 7.5 10 to the power minus 3. That's the dissociation rate and dissociation rate going back and forth. What about going from charge 1 to charge 2? Once again, we are lucky. That value is experimentally known, and that value is essentially given by 6.2 10 to the power minus 8, relates the singly charged to doubly charged molecule. And the same is true for double to triply charged molecules. One thing you immediately see that in each case, there is this concentration of hydrogen. Whatever number of hydrogen you have in the environment, defined by the pH, that will go in here. And as soon as you know that value, rest of those things becomes obvious, because then you can calculate all the other values in a cascaded product. Let me explain how that works. Let's say you're very careful. You haven't put any orange juice, or you haven't bought any orange juice to your lab. Very careful. So you have pure water, and the pure water has pH of 7, as you know. And so therefore you put 10 to the power minus 7 molar, and correspondingly you can relate singly charged, neutral to singly charged to doubly charged, and from doubly charged to the triply charged molecules. The ratios are all given, obvious. And then one thing you immediately see, that for every 100,000, approximately 100,000 singly charged residues, singly charged DNA base, there is one which is not dissociated. So essentially what this is saying, that at pH 7, almost everybody will be at least be singly charged. And what we find here, the statement here, is that a fraction of them are also doubly charged, about 0.62. About half of them are also doubly charged. And triply charged in this condition, negligible. We can forget about it. And so therefore you can immediately solve for this equation. Singly plus doubly charged is equal to the original number, whatever number of dry molecules you put in. The ratio is known. You can solve for this singly and doubly charged. So per base, you'll have to multiply with 1 for singly charged, 2 with doubly charged. And on average, what you find is you have 1.38 Q. So it's approximately 1.5 Q per base pair. Simple example, let's say you have a 100 base pair long DNA that has been diffusing around and eventually has just bound to the sensor surface. How much charge do you expect? Well, you say if the pH is 7, then I expect 100 multiplied by 1.38, 138 equivalent electronic charges. That is how much charge has landed, and therefore, if my sensor is sensitive enough, it may be able to detect that binding. Now, it turns out that the math I just showed you in few lines of algebra, you can essentially write a very simple formula for it, and this is derived in the appendix. So I'll go very quickly. X naught is the original number of this phosphoric acid. X is the one that is still neutral after going through all this dissociation association process. Y1 singly charged, doubly charged, and triply charged. You can solve from the previous equation to see that the value of M, which is just by definition, can be obtained if you know the pK value associated with dissociation constant for Y1, Y2, and Y3. For example, if it is M2 that you are looking for, you want to know how many Y2s you have in the solution, all you have to do is to add pK1 and pK2, just these two terms, not all three. And then I will be 2 multiplied by the pH value of the solution. Once you put it in, you will get 2. And you can see how you do 3 or how you do 1. And once you have this, you can plot this very beautiful curve. It says that as a function of pH, formation relative to PO4, in the beginning, you had almost 100% H3PO4, nothing dissociated at that condition. And then you had singly charged, then you have doubly charged, and finally you have this residue where almost all the hydrogen protons have left, very highly charged here. Remember the calculation we just did in the previous slide? What was the answer? The answer was at pH equals 7, the charge is approximately 1.38, and you can calculate the ratio between the blue and the red at this point at pH is 7 is indeed close to 0.62, and that's what the calculation we did. We did it for one particular value, but of course if you wanted to do it any other pH, for example 6, then you'll say everything is singly charged. If you did it at 8, you'll say everything is doubly charged. So you can see the same length of biomolecule can go from, let's say, 100 length, the charge can go from 100 to 200 simply depending on your pH concentration. Alright, that's about DNAs. DNA binding is necessary for genome sequencing, as we said. Let's think about a protein quickly and see what type of pH dependence does protein has. Again, pH dependence would be something that will perturb the charges associated with the protein. Recall that protein is also a polymer, very similar to the DNA, but the difference is this, that if you made a sort of a ring or a thread, then in that case there would be 4 elements for the DNA with these 4 different colors. For a protein, there are 20 of them. And each one of them can in principle donate or accept electrons. So these individual units are called amino acid. And these amino acids are distinguished by this complex molecule R. Of course, it has the NH2 group on one end and COOH group, carboxyl group on the other hand, but this is the same for everyone more or less. The R is different. There are 20 different versions of R. And so therefore, you can think about this chain having 20 different colored beads for this DNA. And what we want to know that if you have a sequence, then what is the charge? Because once the molecule comes, that is what we'd like to detect through a potentiometric sensor. How do you calculate it? Let's take a prostate-specific antigen. Remember, this is the biomarker that shows up when somebody is an early indicator of prostate cancer. So if we can detect it in blood, that will be very good. And we want to detect it by potentiometric sensor. So therefore, we need to calculate the charge associated with it. Remember, there will be 20 different colors in this biomolecule, which will give its charge. Now, very quickly, you can look it up in a Wikipedia or any other reference material, that these residues, the residue R, is actually, there are quite a different variety. They have very different property. But the important point is, some of them will be positively charged, some of them will be negatively charged, some of them will be uncharged altogether. So as far as potentiometric sensors are concerned, we'll just focus on the charges, focus on the amino acids that are charged. So let's see how to calculate it. So for example, here I have written out all the amino acids that are charged, 3 positively charged and 4 negatively charged. So the blue ones are negatively charged. So these negatively charged each has a pK value. That means it dissociates and associates in water at a certain rate, defined by this potential of K value. And then for each one of them, there is a separate value. And this value is important because this can be singly charged or uncharged. And therefore, you remember that we have a simple formula to know what fraction of them with respect to the original content is charged. Is simply given by m divided by m plus 1, and that depends on pH. Again, this will be in the appendix, so don't worry about it. Just this formula, simple formula will do. And similarly, for positive charges, these 3 positive charges, pK values are known, And so correspondingly, you can find how many of them has actually accepted a proton and thereby have become positive. And so therefore, a combination of positive and negative things overall will tell you, depending on the relative fraction of them, will tell you whether the biomolecule as a whole is positive or negative, or at some point it can even become charge neutral at point of zero charge, at the isoelectric point. So very quickly, an example would help. For example, this is a 261 amino acid in the prostate-specific cancer. I just highlighted D, of course, and then there are, you can see other letters. You can see it almost looks like a code. Not surprising, because the English letter has 26 letters and we have 20 DNA. And so therefore, using the English letter to represent them makes very good sense. Each one of them has a certain amount of charge specific to the pH. Remember, with different pH, it will be slightly different, and you just put it in a calculator and calculate how many positive and negative charges you have. This is a representative typical calculation. What you see that below pH of 6, essentially, or slightly more than 6, things are positive. On average, each molecule is bringing in 10 to 15 unit charge. There is a point when the positive and negative balance each other. So although the molecule is still there, it is as if it disappears from the potentiometric sensor's perspective, disappears from the radar of the potentiometric sensor in some sense. And if you increase the pH, the charges will become negative. And that something is represented by this curve. And in fact, this type of calculation are pretty accurate. So the blue lines are for different types of sensors or different types of proteins. You will be doing it as a homework. You will go to the protein data bank, download the structure, write a little code, and that code will also be provided, and you will be able to essentially calculate this pH specific charge for each one of the biomolecule. And if you just go and compare with experiment, you'll find the experiment to be surprisingly close, because these quantities have been calculated over a long period of time. Alright, so we know now surface charges depend on pH, biomolecule charges, DNA and protein depend on pH. And so we again have salt and we have all these pieces. So now how do we put them together? Turns out to be relatively very simple. This is how. So we are thinking about biomolecules here on the top and a sensor surface, let's say silicon dioxide, where the metal has been replaced. And we have, of course, on the surface itself, also positive and negative charges. And remember, this value depends on the pH itself. And so each one of them, as soon as you tell what the pH is, I can tell you everybody with the charges for all the biomolecules and what the surface charge is, right? So now, this is the formula. And we will not worry about the formula right now. This would be derived in the appendix, but I discussed it a little bit ago. And you can see the important point is that as soon as you know the pH value of the bulk solution, these individual values are all known and tabulated. So you will know what the value of the DNA is. Surface charge correspondingly, do you see the corresponding pH appearing in here? And once you know that value, all other constants are known. You know the surface charge. Taken care of. pH taken care of. Next, this is how it works. So you start with a certain DNA charge. Let's say you have caught 50 DNA on the sensor surface. So for individual DNA, you will have qDNA. You multiply it with 50. That gives you the total charge. Then you look at what the surface charge is on the surface using this formula. Then you calculate, put all the charges together, all the biomolecule charges, which is the DNA. If you had protein around, you would put it in here, and the surface charges, and use the relationship between the potential and the logarithmic of the charge. This you'll see from previous, like 2 lectures before, that there is this relationship between potential and charge. And once you have gotten the potential, then you have to do a self-consistency, because this will change the surface pH. And once you know the surface pH, you will go back and recalculate them. So you can go back and forth and eventually to calculate what the net charge is. Now, of course, if you have salt on top of it, you will have to do the corresponding self-consistent solution. And you will be doing it in a homework in the biosensor lab available in NanoHub. And once the charges have been calculated in a stable way, you can immediately calculate the charge in the MOSFET, which is the oxide capacitance multiplied by the self-consistent potential here, and the corresponding charges. Therefore, this directly reflects the charges of the biomolecule. This is good, and it turns out that it can interpret experiments pretty consistently. I'll give you an example. So for example, this is the biomolecules like this, which has come and landed on a sensor surface. And for a specific value of pH, for every value of pH, it can either be positive or negative. And so therefore, the corresponding transistor which is sitting underneath can either be in the depletion or in the accumulation. This, by the way, only happens for protein, which can have positive and negative molecule charges, not for DNA, which is always negative. If you don't remember what accumulation was, just to remind you that accumulation is whatever charge you have here. For example, you have negative charge. If you have more of it, that's accumulation, that's this branch. On the other hand, when the pH changes and the biomolecule protein becomes positive, of course, you cannot change the transistor itself. So in that case, the type of the charge carriers will invert, and that's what this depletion is all about. And if you look at experiments, the experimental results will be pretty close. And that's what always surprises me, how very simple concepts like this can explain very complicated experiment with lots of things going on pretty nicely. One final concept, and then I'll be done. Remember this surface charge. Surface charge is great for pH sensors, pH monitors. I mean, that's very good. But in this particular case, I just want to see the blue molecules. I don't care about the surface charges because they are interfering. They are producing a parasitic current, giving the impression that as if the molecules have landed, which is not the case at all. So then, how do I make this red disappear, the surface charge disappear? Well, you know the answer. The answer is that for that particular surface, like on silicon dioxide, there is a point of zero charge. For example, in this case, let's say the point of zero charge is 4. So if you bring the pH to 4, remember originally we are not planning to change the pH because we said we'll be very careful, want to work with pure water. But it turns out that if you do change the pH, then all of a sudden the surface charge will disappear. There will be still positive and negative charges. They will balance each other out. And therefore, this red line will disappear. And the whole charge associated with the blue molecules will shine through, will essentially get reflected on the sensor surface itself. Of course, save the part associated which has already been consumed by the salt itself, which is taken away by the salt. Now, this particular amount of charge would be very good, but remember, it's very important that the DNA is not too far away from the isoelectric point. It has all these positive and negative charges that allows it to fold in a particular way. And if you move things out too much, everything becomes very positive, then the shape may not remain the same. And therefore, the antibody which is supposed to catch it may not recognize the shape. And so therefore, you may not always want to go for maximum charge. A little bit below may sometimes still suppress the surface charge, but still be good for detection and capture. Let me end then. So my conclusions are the following. The conclusions are that many biomolecules are in charge in solution. Not everybody. You saw that part of the amino acid even you had put in the solution, they did not get charged. But DNA and a large fraction of 7 molecules in the amino acid in the protein actually got charged. And these charges are about 1 to 2 for DNA, negative 1 to 2 by the way. And on the other hand, protein charge can go from positive to negative depending on the pH you have. And at the point at which the protein charge vanishes is called the isoelectric point. We have to be very careful to stay away from the isoelectric point, because at isoelectric point, the protein molecule disappears from the sensor response, because the charge is essentially zero, and potentiometric sensor only sees charge and nothing else. Now it turns out that if you do some charge calculation, compare with experiment for DNA, as you will do in the homework, turns out that the results would be pretty good, and you'll be actually impressed how close it is to the experimental value. Finally, I want to caution you a little bit. You see, we said for a given pH, the solution develops a surface charge, the biomolecules, the receptors will have a certain amount of charge. Everything is nice and good. Now let's say with a pipette you put a little bit of analyte molecule in. If you are not careful, maybe the analyte molecule had some DNA, which is something you are trying to detect, but somehow if it disturbs the pH, remember pH is essentially just protons. The protons will diffuse very quickly to the sensor surface. It will change the surface charge. It will change the receptors, charges of the receptors, giving an impression as if the biomolecule has come and landed on the surface, because the MOSFET doesn't know any better. And this false impression can give you, false impression that the biomolecule has been captured. Looks like it's one has to be very careful to do the experiment right. But it will turn out, as I'll show you in lecture 28, this parasitic effect is the basis of all modern genome sequencers. Something that looks like a accidental thing, something that you didn't want. Remember the pH disturbance sort of being a vanguard of the molecules that are coming later on? That turns out to be basis of the most modern technology we have. But you have to wait a little bit until we get to that point. Until next time, take care.